And it's gone. There it is. So, the graph shows, again, sales of shoes in a store over a certain period of time in weeks. Oh, man. One of those days. Based on the graph, select each true statement. Each true statement, what does that mean?
More than one.
More than one, exactly. We've got more than one answer. Good call on that. I love the literal interpretation over here too. That's great, absolutely. More than one answer. Let's take a look. Option A says the sales of shoes remained the same between weeks 1 and 2. Go ahead and find the interval or the space between weeks 1 and 2 on this graph. We're looking down at the x-axis where we have weeks. We're going to look in between 1 week, and 2 weeks. So that small section of the graph right there. What's happening with our graph in that identified section? What does that part of the graph look like? Does it look straight? Does it look flat? Does it look curved? Let's describe it. What does it look like? It looks flat, right? I'm talking about just this section here in red. From 1 week to 2 week. Right after 2 weeks, we start that curve going upward. But from 1 week to 2 weeks, that looks just like a straight up flat line, which means that our sales must have stayed stagnant. We didn't have any new sales within that time. So the sale of shoes remained the same between weeks 1 and 2. That's absolutely correct. We'll mark that one first. Anyone unclear on how we identified that as an answer? Good. The second one, the sale of shoes increased between weeks 3 and 4. Let's find weeks 3 and 4. Here's my interval now. What's happening to the graph in this interval? It's increasing, right? It's going upwards, sloping up. So that one's definitely going to be correct as well. We see that it's increasing in between weeks 3 and 4. So this problem is all about understanding how to read a graph. Take a look at the last one. The sale of shoes decreased between weeks 4 and 5. I'm going to highlight the section between 4 and 5. It's that rectangle in yellow. Does it look like the sale of shoes is decreasing in that amount of time? No, it looks like after 5 weeks, it starts to go down. After 6 weeks, it's still going down. But from 4 to 5, it's still increasing. That one's not going to be one of our answers there. Andy? Yeah. Questions on how we interpreted the graph here in number 1. Just trying to understand. It's kind of like that airplane problem where the graph went up when the airplane was ascending. The graph turned flat when it stayed level in the air, and then it went down when the plane started descending. Hopefully that sounds familiar to you. Number 2, we've got a linear function here. How do we know this function is linear without an equation? Straight line, nice and simple, right? Linear means line, straight line. So when we have a straight line and we're trying to find the equation, what 2 pieces of information from yesterday do we need to find? Should say, what 2 letters do we need to find? M and B. Noah. Yeah, when Andy comes back. Just looking at this graph, what's my B value?
1.
Positive 1. How do we know it's positive 1? Well, it's where the line intersects or crosses the y-axis, right? That's our y-intercept, is 1. So the fact that we know that our b is 1, that means that our equation, whatever the slope ends up being, our equation has to end in plus 1. So if we look at our answer choices right away, which ones can we get rid of? A and D, right? That one goes away. That one goes away. Because we don't have plus 1 as our b value. We have them in the other 2, so now it's just between b and c. Got to find the slope to determine which one is correct. Before we do rise over run, is this going to have a negative slope or a positive slope? Is our slope here going to be negative or positive? What do you think?
Negative.
Negative. Why do you say negative, Mason?
Going left to right.
That's right. From left to right, we're going downhill, so our slope's going to be negative. Now let's do rise over run. We've got a point right there. Obviously, we've got our y-intercept. How many units do we need to rise up? 2. 1, 2. 2 units up. And how many units now do we have to go to the left? 3. 1, 2, 3 units to the left. So our rise over run is going to be what? 2 over 3. Are you sure it's not 3 over 2?
No.
Good, yeah, it's not 3 over 2, right? Rise, our change in y, always has to go over our run, which is our change in x. So 2 over 3, we have to make sure that it's negative. So which answer choice is correct, B or C? B, we've got negative 2 over 3. That's the slope that we found by doing rise over run. There's our answer. Questions on 2 I can answer. Now we're going a little fast, but I want you to have time to work on your own too. Hopefully this at least jogs some of those memories that we have from term 2. I know it's been a while. Going down to 3. Jeremy has shown the graph below and asked to write an equation. Jeremy writes the equation 1 plus 1/2 x. Now, the way that this is worded is a little bit weird, but we can just rearrange this order to make it more appealing to our eyes, right? We can take this positive 1 and this positive 1/2 x, and we can switch them around. 1/2 x plus 1. Does not change our equation at all, and especially since both terms are positive, we don't have to worry about making sure that negative that we may have would need to stay in front. We don't have to worry about that. So the question is Jeremy's equation incorrect? If so, what is the correct equation? Well, let's take a look at the graph. What's my y-intercept of this graph? Positive 1. So far, his equation looks good, right? That plus 1 on the end matches up with the one that we found. Everyone see that? Now, what's my rise going to be from one point to the next? How many do we have to rise up? 3?
2.
1, 2 units up. How many units do we have to go over? Just 1 unit over. Rise over run gives us 2 over 1, which is just 2. Did Jeremy write the correct slope in his equation?
No.
No. What mistake did he make?
He put 1 over 2.
He put run over rise. Exactly, Azalea. He put 1 over 2 instead of putting 2 over 1. That's a mistake that I saw you guys make a lot. Well, not necessarily you specifically, but students in general during this unit was forgetting that it's rise over run and not run over rise. If you ever forget, just remember, if you're going to go on a run, you have to rise in the morning first before you can go on a run, right? So first you rise, then you can run. So which of these answer choices is correct? Let's see. A says the slope of the graph is actually 2. The equation should be 1 plus 2x. Does that sound right to you?
Yeah.
Sure does. But let's take a look at the others. The y-intercept of the graph is 0. Is that the case? No, definitely not. The slope of the graph is negative. Well, should it be negative based on what we see here? No, from left to right we're going uphill. So that one's not right. Option D says the y-intercept is at 1/2. Is that true? No, it's at 1. We established that first thing. A must be our answer. Just got the wrong slope. Nothing too crazy. Questions on 3. Good, now we're going to 4. We got a table. Whenever we see a table, our brain should just automatically draw these little arrows from the first data point to the next data point. Because whatever we have to do with this problem, that's most likely going to be part of it. But let's see. This table shows the linear relationship, linear, no exponents, right, of the cost in dollars, y, of buying snack packets purchased, which is x. So x is our number of snacks, y is our total cost. We have to find and enter the rate of change of the cost per snack. Rate of change. Does anyone remember another word for that phrase? Rate of change. There's a bunch of different... Ratio. Good. It's definitely going to be a ratio of the change in y over the change in x. What do we call that? Good. A unit rate, also known as slope. We know this. Rate of change, unit rate, slope, they are all the exact same thing. The only times we use rate of change and unit rate is typically when we're talking about a word problem within a specific context, right? Thank you. So in this context, we've got snack packets costing a certain amount. What's my change in y from $1.60 to $2.40? Plus 0.80. That's right, 80 cents. What's my change in y? Or my change in x from 2 to 3? Plus 1. Now, let me give you the second page real quick. Notice how we go from 2 to 3, and then from 3 we go to 5. That's plus 2, right? Uh-oh, it looks like we might have something weird going on here, but maybe not. How do we get from 2.4 to 4.0? What's that a change of? Plus 1.60. Right? From 5 to 8, that's plus 3. What's 4 to 640? $2.40. So even though our change in y and our change in x are different, what do we notice about the relationship between them? Starts with a P. Good, they're proportional, right? 0.8 over 1 is the same as 1.6 over 2, which is the same as 2.4 over 3. They're equivalent fractions, they're proportional fractions, so we do still have a linear function here. But the question is, what's the rate of change per snack? So 2 snacks is $1.60. How many is 1 snacks? 0.80. Right? If we were to take this table back one step, if we found the number where x is equal to 1, we would have to subtract 0.8 from 1.6. That gives us 0.8. So how much would 0 snacks cost then, if we continued this pattern? $0, right? If you don't buy any snacks, you don't spend any money. Nice and proportional. Right? There's no initial value. There's no like $2 snack fee that you have to pay just to be able to buy snacks. That would be a non-proportional function. But here, we got proportional. $0.8 per snack. We got a unit rate. We need units. 0.80. All right, that's all we're going to talk about for right now. Hopefully that helps refresh your memory a bit.